Okay, so last class we discussed about the properties of real numbers, and then we study the important axiom, that is LUB axiom. So now in this class we study some two applications of LUB axiom. It's very important applications of LUB axiom. The first one is Archimedean property. Okay, so this is very important application of LUB axiom. Okay, that axiom is maybe we state as a theorem. Actually, this theorem is Archimedean property. Archimedean property. In short, we denote AP property. So AP means Archimedean property. So this is an application of LUB axiom. So what the LUB axiom says? If we give any non-empty bounded above subset, it has a least upper bound. Now, so using that, what is the Archimedean property say? There are two forms there. For Archimedean property, there are two forms. The two forms are equivalent form. So what is the first Archimedean principle? That is AP1. Archimedean property 1, it says the natural number is not bounded above. The n is not bounded above in R. Okay, so what do you mean by not bounded above? We cannot find any alpha such that x less than or equal to alpha for every x in n. Okay, this is the first Archimedean property. N is not bounded above. The second Archimedean property, second form. Okay, anyway, the first form and second form are equivalent. Now the second form says, given any two real number, given x and y in R with the x is positive, then we can find a natural number. Then there exists some natural number n in n such that n into x should be strictly greater than y. So this x should be positive number. So given any two real number with x positive, then we can find a natural number n such that nx greater than y. And this satisfies the condition nx greater than y. It's very, very, very important property. So in a sequence, we use Archimedean property simultaneously. Okay, if we take any problem, so either we can use directly or indirectly we use the Archimedean property. So Archimedean property says given any two real number and the one of the real number is positive, then we can find a natural number such that nx greater than y. Okay, now we can easily prove this by contradiction. Okay, so anyway, proof of the first one. So how to prove the set of all natural number is not bounded above? So proof, very simple. Proof of the Archimedean property, first form. Suppose not. Suppose you assume that the given statement is false. That means what? What is the negation of n is not bounded above? N is bounded above. N is bounded above in R. So what do you mean by definition of bounded above? There is a real number alpha in R such that if you take any n in n such that n should be less than or equal to alpha. That is, a bounded above means that at least one upper bound exists. So there exists an alpha such that if we take any natural number is always less than or equal to alpha. But if we take alpha equal to some other number, so what you take? You take n plus 1. So okay. So alpha is an upper bound. Suppose if you remove one small quantity from alpha, that is not an upper bound. Therefore, since alpha is an upper bound, or So okay, anyway, we can use the Archimedes property. Say we have to use the LUB axiom, right? So application of LUB axiom. So since here n is a subset of R and n is a bounded above by LUB axiom, n has a least element, that is LUB. So we call the LUB of n, we call alpha. Okay, LUB exists because by LUB axiom, every bounded above subset has a LUB. We call alpha is the LUB of natural number. So that means what? Every natural number is always less than or equal to alpha. So if you consider alpha minus 1, since alpha is the least upper bound, if you remove some partial upon some positive quantity, 1 is not an upper bound. Is not an upper bound. Because alpha is the least one, if you remove some small positive quantity, that number is not an upper bound of natural number. So what is the meaning of not an upper bound? There is a natural number which is bigger than alpha minus 1. So that is alpha is here. So suppose alpha minus 1 is here. Since alpha minus 1 is not an upper bound, that means what? At least one elements should be appear after this alpha minus 1. So that is there exists n in n such that this alpha minus 1 is smaller than n. So this implies that alpha is strictly less than, just add 1 both the side, we get this one. So which is a contradiction. What is the contradiction? Since here we mentioned that every natural number is always less than or equal to alpha, but now we find one natural number, namely n plus 1, which is bigger than alpha, which is a contradiction to our assumption. So what is our assumption? We assume that n is bounded above, we get a contradiction. Therefore n should be not bounded above. Natural number is not bounded above in R. So one of the application of LUB axiom. Now the second form also again we have to assume that suppose not, and then we get a contradiction. So that means what? There is a x and y with the x positive, such that if we take any natural number such that nx less than or equal to y, then you will get a what is actually first, what is the negation of the given statement. So now the second form of argument property AP2, it is actually given that if we take any x comma y in R with x greater than 0, then there exists n in n such that n into x greater than y. So this is a property. Now what is the negation of this statement? So there exists x comma y in R cross R. So why? Because I am writing this. So usually there exists means is denote only one number, but here we use two numbers. So usually we omit or we, so there exists means we have to denote only one number. So writing this there exists x comma y in R2 is not meaningful. Therefore you have to make as a one element. Therefore look at the ordered pair, but take R cross R. Now we get x in R, y in R. The same way. So there exists x comma y because this is for every. Otherwise, if we write this for every x comma y in R cross R, simply with the x positive, and if we take, because negation of there exists is for every n in n, if we take any n such that nx is less than or equal to y. Since nx is less than or equal to y, since x is a non-zero number because positive, therefore multiply 1 by x both side, we get n less than or equal to y by x for every natural number. So that means what? From this we get this y by x is an upper bound because every natural number is less than or equal to this number. Therefore it's an upper bound of natural number. So this implies that we have at least one upper bound. Therefore the natural number is bounded above, which is a contradiction because we already know that n natural number is not bounded above in R. So which is a contradiction. So this notation denotes contradiction. So therefore our assumption is wrong. What is our assumption? This is our assumption. Suppose not, we get contradiction. Therefore the given statement is true. Okay. So actually these two forms are equivalent. We assume the form 1, we prove form 2. Again we assume form 2, we prove form 1. Therefore these two forms are equivalent. Anyway, this we call either the first statement is Archimedean property or the second statement is the Archimedean property. Anyway, both the statements are equivalent statement. Okay. That is a theorem says. Now there are some applications of this Archimedean property. So this Archimedean property is very important. Either natural number is not bounded above or given any two real number with one real number is positive, then we can always find a natural number n such that nx greater than y. So we can simply say given any single real number, so that is a special case. So given a single real number r, we can find a natural number n in n such that n is greater than x. Why? How this is true? Because now we take y equal to 1 and we know that 1 is a natural number. Now apply Archimedes property for these two real number, we get their axis n in n such that n into the positive number. What is the positive number here? 1. N into 1 is strictly greater than x. So that is nx greater than x. So therefore, given any single real number, we can always find a natural number n such that n is greater than x. So some special corollary of the given Archimedes property. Because we know that 1 is a real number, positive real number. Now apply Archimedes property for these two real number, we get the statement. Okay. This is also one of the Archimedes property. Okay. Now he states some theorems. It's very important theorems. What the theorem says, suppose just now we proved that given any single real number, so that is given x positive, so that is x is a real number which is positive, then there exists a natural number. So given any positive real number, we can always find a natural number n in n such that satisfy the condition is x is bigger than 1 by n. So always true. Why? Again, since 1 is any so this is just cross multiply, we get nx is greater than 1, right? So we get this by applying Archimedes property of two real number, namely x and 1. So anyway x is positive. So now apply these two, take these two real number and then apply Archimedes property, we get this one. From this we get this one. So just to multiply 1 by n both sides we get, because n is positive number, if you multiply 1 by n, the inequality does not change. Okay, this is the first theorem. So this is a simple deduction of the Archimedes property. Okay, so that is first one. Now the second theorem, suppose if you take x is positive, let x greater than or equal to 0, then when we say the number is 0, then x equal to 0 if and only if, so proving a number is 0 if and only if it is enough to prove that for each n in n, we have x is less than or equal to 1 by n. So if we prove x less than or equal to 1 by n for all n, then x should be 0. If x equal to 0, then x less than or equal to 1 by n for all n. So this is important here. So provided x should be positive real number. So when we say a positive or non-negative real number, it becomes 0 if that number is less than or equal to 1 by n for all n. Okay. So what is the proof? This is very, already I said that first one is very simple. Now what is the proof of the second one? Very simple. So it is given that x greater than or equal to 0. So from that, what is the meaning of this? Either x greater than 0 or x equal to 0. That is the meaning of this x greater than or equal to 0. Now what we got to prove? We got to prove x equal to 0. Okay. Suppose this is not happen. Suppose therefore this is not happen, then x greater than 0 is true. Then we will get some contradiction. Therefore this will not be true. Therefore x should be 0. That is the proof. So what is the proof? Suppose x is strictly greater than 0. So proof of this second, suppose x is strictly greater than 0. Okay. Now by property 1, by statement 1, given any positive numeral, we have a there exists n in n such that x is greater than we take some, okay, 1 by n. Okay. So anyway, so we assume okay, we prove if and only first we assume this, we have to prove this, right? So we assume that x is less than or equal to 1 by n for all n. We have to prove x equal to 0. Suppose x not equal to 0, now we get this one, but we know that this x should be always less than or equal to 1 by n. But here we get this x is greater than 1 by n for some n, which is a contradiction to our assumption, therefore which is a contradiction. So this is our assumption. Okay, this is our assumption. We have to prove x equal to 0. Suppose x not equal to 0, then x should be positive. If x is positive, by the first part, we get there is a natural number such that x is bigger than 1 by n, which is a contradiction to our assumption. So what is the assumption? X less than or equal to 1 by n for all n. But here we get x is bigger than 1 by n for some n. For this particular n, maybe we can take some capital N. So there is some capital N such this is happening. So which is the contradiction to our assumption. Therefore, our assumption is wrong. Therefore, x should be 0. Okay. Now the second part. Suppose we have to assume x equal to 0. We have to prove that x should be less than or equal to 1 by n for all n. So that is trivial. Since x equal to 0, the 1 by n's are always greater than or equal to, because all 1 by n's are positive number. Because natural numbers are positive, therefore 1 by n's are positive. Therefore, this is true. Therefore, we can take this one, x less than or equal to 1 by n. So that converse part is trivial. Okay. So therefore, this is very important thing. So whenever you want to prove a positive number is 0, it is enough to prove that that number is less than or equal to 1 by n for all n. Okay. So it's very important. So there are now so far we proved two criteria to say two numbers are equal. So suppose this is x equal to 0 if and only if this x is 1 by n for all n. Now, so maybe quickly we recall, when we say two numbers are equal, so we want to prove two numbers a and b are equal, it is enough to prove that a less than or equal to b and b less than or equal to a. Okay, this is a idea to prove two numbers are equal. So proving two numbers are equal, it is enough to prove that a minus b is 0. Yes, if you prove a minus b is 0, then a equal to b we get, right? Now apply this theorem. So proving a number, this number equal to 0, it is enough to prove that this a minus b is less than or equal to 1 by n for all n in n. So if you prove this, we get a equal to b. So no need to prove this a less than or equal to b and b less than or equal to b. Anyway, we can prove this way also, but this another way of proving a equal to b is a minus b equal to 0. So that is nothing but a minus b is less than or equal to 1 by n for all n. Okay, so this is a very important point. So proving a number is 0, it is enough to prove that the number is less than or equal to 1 by n for all n. Okay. Now use this result. Now we have to prove that LEB of 0, 1. Already we proved that last class we proved that the open interval 0, 1, right? So the LEB of the interval 0, 1 is 1, and then the GLEB of the interval 0, 1 is 0. Okay. Using these two results, we can easily prove that 1 is the least upper bound of this 0 comma 1, 0 is the greatest lower bound of 0 comma 1. Okay, anyway, now we have some typical use of this Archimedes property. So where this Archimedes property is, so we solve some problems. So exercise is very important thing. We can easily understand where this Archimedes properties applies. So first we take, I take some intervals. Jn is nothing but open interval 0 comma 1 by n. So that is, what is j1? J1 is nothing but 0 comma 1. 1 by 1 is 1. What is j2? J2 is nothing but 0 comma 1 by 2. What is j3? 0 comma 1 by 3. Okay, suppose if you look at in the picture, so this is 0 and this is 1. So j1 is nothing but 0 to 1. What is j2? This is 1 by 2. So this is j2. And this is 1 by 3. Therefore, this is j3. Now, and so on. So now you take intersection of all the jn's. Intersection of jn, where n in n. So what is the common? So first this is j1 and this is j2 and this is j3 and this is and so on. So take intersection of all the things, what will get? Can anyone? What is the intersection? Anyway, look at this, 0 is not there. 0 is open. Okay. So what is that? Should be empty set. There is no element in common. Why? Suppose the intersection is non-empty, we get a contradiction. So suppose the intersection is non-empty. Intersection Jn is non-empty. Then non-empty means what? There is a common element to all the interval. That is, there exists an element x in the intersection n in n. Okay, so that means what? X is an intersection means what? X belongs to all the jn's. Implies that x belongs to jn for all n in n. So, but what is jn? So implies x belongs to, what is jn? 0 comma 1 by n for all n in n. So this implies what? X lies between n for x strictly less than x, strictly less than 1 by n for all n in n. So suppose we have a inequality like this, a less than b, we can write a less than or equal to b. So therefore we can include this. It's not an issue. So now look at this inequality. The number x less than or equal to 1 by n for all n. By already we know that a number is less than or equal to 1 by n for all n, then the number should be 0, right? Therefore we get x should be 0, but we know that x should be strictly positive here. So we get a contradiction. Because from this inequality we get x equal to 0, but this inequality says x should be strictly greater than 0, we get a contradiction. Therefore our assumption is wrong. So what is our assumption? We assume that the intersection is non-empty, we get a contradiction. Therefore the intersection should be empty set. So if we take the interval like open 0, open 1 by n, the intersection should be empty set. Suppose if we include 0 and take 1 by n is open. Suppose if we take this is jn, now the intersection of jn should be singleton 0. So only contains 0. Okay. Now the next example, if we take jn's are close to n, comma infinity. So that means, so this is 0. So for all natural number, we define jn equal. So what is j1? J1 is nothing but 1 comma infinity. So this is 1 and this entire thing. So what is j2 is 2 comma infinity. So that is 2 is here and this is another part. And j3 is 3 comma infinity. Now first is, what is the intersection? intersection of jn's. What is it? Take the common. This first one is j1, from this one is j2, from this is j3, and so on. Now you take the intersection. What is the common? It's again empty. It's an empty set. Or if you take intersection of all the jn's, it should be intersection is empty. Why is an empty? So how to prove? Suppose non-empty. Suppose the intersection of jn is non-empty for all n. So non-empty means what? At least one elements in the intersection, that is there exists x in the intersection of jn's, where n in n. So x in the intersection means what? Implies that x belongs to jn for all jn, for all n in n. So that means what? X belongs to what is jn? Close to n, open infinity. Okay, for all n in n. So that means what? We have x in this interval means what? X less than or equal to, sorry, n less than or equal to x for all n in n. Got it? So from this, since n is a positive number, so x is bigger than n. Therefore, definitely x should be non-zero number, because natural numbers are always start from 1, right? Therefore, n is bigger than 1, but x is bigger than or equal to n. Therefore, x should be bigger than or equal to 1. Therefore, it's a non-zero number. Now, we can take other ways. We can say simply we can stop here, and then we can say since any natural number is less than or equal to x, that means what? X is an, so every natural number is always less than x. It implies that x is an upper bound. X is an upper bound of the natural number. That means what? Implies that n is bounded above. Because if you have at least one upper bound, then that set should be bounded above. Bounded above in R, which is a contradiction, because already we know that by Archimedes property says n is not bounded above, but we hear it, which is a contradiction. So why we get a contradiction? Because of our assumption. What is our assumption? If the intersection is non-empty, we get a contradiction. Therefore, intersection should be empty. So now we take another example. So these are all application of Archimedes properties. Now if we take third example, if we take let jn equal to the interval open 1 by n, comma 1. If we take this interval, so that means what is j1? So j1 is nothing but just a open interval 1 comma 1. It's nothing but just a empty set, because there is no element here, therefore it's empty set. Now what is j2 is 1 by 2 comma 1 in the interval. What is j3? 1 by 3 comma 1. So for example, look at the graph. So this is 0 and this is 1. So this is 1 by 2. So this is j2. This is 1 by 3. And this is j2, j3 and j4, j5 and so on. Now what I am taking, so take the union of all the j's, what you will get. So therefore union of all the j's, where n in n. So anyway, this is fixed, right? So this is j1 and this is j2, this is j3 and this is j4 and this is j5. So you take all the unions, is cover entire space up to 0 to 1, but here open 1, right? Therefore this is nothing but open 0 comma 1. So how to prove this one? So how to prove this equal to this? So that means we have to prove if we take any element here, that element should be in the set 0 to 1. Again, if you take any element here, that element should be in the union. So that is a, so how to prove two sets are equal? We have to prove two containment. Either we have to prove A is a subset of B and then B is a subset of A. Okay. Now, so we guess that the answer is 0 to 1, open 0, open 1. Now how to prove this one? Suppose we start with the element in the one side. So we take arbitrary element x in the union of jn's. So n in n. Now what we have to prove? We have to prove x belongs to 0 to 1. Now by the definition, x is in the union Therefore, x belongs to Jn for some n. It is intersection, then it belongs to all n. It is in the union, therefore x belongs to Jn for some n in n. So what is Jn? Jn is nothing but 1 by n comma 1. Therefore x lies here. Therefore 1 by n strictly less than x, strictly less than 1. But we know that all the 1 by n's are positive. Therefore 0 strictly less than x less than 1 implies that x belongs to open interval 0 comma 1. Therefore we start with the element here and then we prove that that element is here. Therefore this union is subset of 0 to 1. Now conversely, we take element y in the open interval 0 comma 1. We have to prove that y belongs to the union. So it is enough to prove that y belongs to one of the j's. Okay, so from this y belongs to here, therefore 0 strictly less than y strictly less than 1. So we know that by Archimedes property again. So given any positive real number, we can find a natural number n in n such that this y is greater than 1 by. So look at this. Already we proved that given any x positive, look at this. Given any positive real number, we can find a natural number n such that n is bigger than 1 by n. Okay, so using that, we know that this y should be, therefore this should be 1 by n. And but y always less than 1. Therefore now the y is bigger than 1 by n for some n. Okay, but this inequality says that y is strictly less than. Therefore y belongs to this interval, that is in the interval 1 by n comma 1. This is nothing but Jn. So now we prove that y belongs to Jn for some Jn. Therefore y belongs to the union of all the things. So therefore we get y is a member of union of Jn. Since y is in one Jn, therefore it is the union. Therefore we start with the arbitrary element in the open interval 0 comma 1. Now we prove that that element is here. Therefore we prove that two containment. Therefore the union of Jn is 0 to 1. Okay, next. In general, we say that is another exercise, simply consequence of that one. It's also very important. Suppose show that two numbers a and b. So show that for a comma b in R such that a less than or equal to b if and only if a less than or equal to b plus epsilon for any epsilon positive, for any epsilon greater than 0. So, but in the previously we proved that a less than or equal to b plus 1 by n for all n. But instead of 1 by n, now we take any epsilon positive. Suppose this has happened, then a should be less than or equal to b. If a less than or equal to b, then a should be less than or equal to a plus epsilon for every epsilon. So proof is very simple. So proof of this one. First assume that a less than or equal to b. Assume a less than or equal to b. We have to prove that for any positive all epsilon, we have to prove this. So since we know that b is always strictly less than b plus epsilon, if you provided epsilon is positive, if I add the positive quantity to b plus epsilon is bigger than b. Therefore now by transitivity we get a less than or equal to b plus epsilon. Now we prove that this in implication. Now conversely assume a less than or equal to b plus epsilon for any epsilon or for all epsilon positive, then this is true. And what we have to prove? We have to prove that a less than or equal to b. And already we know that if a less than or equal to b plus 1 by n for all n, then we know that a less than or equal to b. Now we have to change this inequality to in terms of natural number. Okay, it's given that epsilon is positive. So by known theorem, if epsilon is a positive real number, then there is a natural number n in n such that epsilon is bigger than 1 by n, right? Just now we proved. Instead of x, we have epsilon. So any real number positive, you can find a natural number n such that this is satisfied. Now just add okay, anyway, so we get n into epsilon is bigger than 1 because n is a n is a natural number positive. Therefore, n is bigger than 1 by epsilon. Because epsilon also positive, if you multiply 1 by epsilon, the inequality will not change. Therefore, we get this one. Now add b both the side, because so therefore what you'll get, we know that a is less than or equal to b plus epsilon, we know, but okay, so what I'm going to show, this is less than or equal to, okay, I did some mistake, right? Okay, what I'm, so anyway, we have to apply arithmetic property. N into epsilon is bigger than, okay. Okay, this is less than or equal to 1 by n. So we have to prove that this is this thing. So that means what we have to prove, epsilon is less than or equal to 1 by n. So that is, yeah, correct. So we have to prove n is bigger than epsilon. Okay, this is not true in general. Okay, I did some mistake. Okay. So we have to assume that a less than or equal to b plus epsilon for every epsilon positive. We have to prove that a less than or equal to b. Okay. So we have to apply. Okay, otherwise we have to go some other way. Okay, take to apply arithmetic property for this given epsilon positive, there is a natural number n such that n into epsilon is greater than, otherwise, okay. Okay, so okay, we have some, we need some time. Okay, anyway, so just assume the result. Whenever a less than or equal to b, if and only if a less than or equal to b plus epsilon for every epsilon, that is very important, for every epsilon positive, not for single epsilon. Okay, these are all useful result to prove the inequality a less than or equal to b. Okay, so now we have important thing. Q is dense. What is Q dense? Given any two real number, there is a irrational number in between these two real numbers. So that is a theorem. The theorem is density of Q in R. Density of Q in R. So that is what, given any two real number x and y with x less than y, you can always find a rational numbers in between x and y. So that is given any a and b, given any a and b in R with a less than b, with a is strictly less than b, then there is a rational number. There exists some R from rational number such that the R lies between a and b. That is, a is strictly less than R, strictly less than b. So this is a density. So given any two real number, we can always find a rational numbers in between. So for example, this is a one real number. If you take very small another real number, we can always find a rational number R in between. We can always find a R here in between a and b. So that is a density of Q. So similarly, we can define the density of Q complement. So that is, given any two real number, we can find a irrational number between these two real number. Okay, suppose we have some two real number a and b, we can find a irrational number in between two rational numbers. That is the density of Q complement. Very important. Okay. Okay. Now, almost we discuss some basic things, and I hope you know everyone know about the interval. Okay. So quickly we recall what is an interval. So open interval a comma b, closed interval a comma b, all the things. Okay. So close to a comma close to b is a closed interval, is nothing but collection of all real numbers lies between a and b, including a and including b is a closed interval. Open interval means all the real numbers between a and b, excluding a and b. Set of all real number which is a strictly less than x, strictly less than b. Suppose if we take one side closed, one side is open. So this is the open closed interval, that is collection of all real numbers between including a but excluding b. So open closed interval, or sometimes called a mixed interval. Suppose this side is open and this side is closed, then we are collecting the real numbers between a and b, including b, excluding a. Okay, now if suppose if both the endpoints are finite value, this is the case. Suppose one endpoint is infinite, then what will happen? So what is the definition? So that is closed interval a comma infinity open. So infinity is not a number, it's just a symbol. So this is nothing but collection of all real numbers which is bigger than or equal to a. That is, this is only one condition. Don't write this is strictly greater than epsilon or something, because epsilon is not a number. We can compare between two real numbers. Okay, so this is the case. Suppose if you take minus infinity comma open a, so all the real numbers which is less than a, that is set of all real numbers x, that number is strictly greater than, strictly less than a. So these are all type of intervals. So if you take both the side, both the endpoints are plus infinity and minus infinity, this is nothing but real number r, real line. Okay. So the next one is important theorem, nested interval theorem. Suppose we have a sequence of intervals, closed intervals, and this contained in decreasing order. So the theorem is called a nested interval. Nested interval theorem. So the nested interval theorem says we have a closed intervals. So let Jn is a closed interval. We call some an comma bn. J1 is A1 B1, J2 is A2 B2, J3 is A3 B3, like this. So B intervals in R. Okay, such that the intervals are decreasing. That is Jn plus 1 is contained in Jn, such that this Jn plus 1 interval is contained in Jn interval. So this is a decreasing sequence of intervals for all n. Then the intersection contains only one element. Then the nested interval theorem says then the intersection of all the Jn's contains at least a non-empty set. So now it's a non-empty set. Therefore, definitely at least one element in the intersection. So when this intersection contains only one element, the length should be approaches to 0. What is the length? The bn minus an. So this approaches to 0. So that is if you take the more intervals, the length of the interval very close to 0, then the intersection contains precisely one element. That is a nested interval theorem. But nested interval theorem says if you take the decreasing sequence of intervals, closed intervals, the intersection contains at least one element. Okay, now maybe I'll leave the exercise to, okay, we'll show the one more important example to find the LEB of the GLEB of the set. Example, show that GLUB of the set collection of all 1 by n such that n in n is 0. we have to show that the greatest lower bound of this set is 0. So how to prove this one? So first we call this set is some set A. So let A equal to the given set of all 1 by n's n in natural number. So if substitute n equal to 1, we have 1. If substitute n equal to 2, we have 1 by 2, 1 by 3, 1 by 4, and so on. So this A contains all the 1 by n's. Now clearly 1 is an upper bound, and then even 1 is in the set, therefore 1 is the least upper bound. We have to show that 0 is the greatest lower bound. First of all, we have to show that 0 is the lower bound, since all the 1 by n's are positive. Right, because we know that all the natural numbers are positive, therefore all the 1 by n's are bigger than 0. Therefore 0 is a lower bound. Lower bound of the set A. But we have to show that 0 is the greatest lower bound. So that means what we have to show? If we give some other lower bound, then suppose if we take B is a lower bound, then B is smaller than 0. We have to prove. Okay. Suppose 0 is some other lower bound. Suppose B is a lower bound of A. We have to prove that 0 is bigger than B. Since B is a lower bound, then what can you say about this? So B is less than or equal to 1 by n for all n. By the definition of lower bound, every element of A should be bigger than B. Now we have to prove that. To prove B is strictly less than or equal to 0. We have to prove this. We have to prove 0 is a bigger. It is enough to prove if we take some other lower bound B should be less than or equal to 0. Suppose not. Suppose B is not negative. Then what will get? B should be strictly greater than 0. Okay. So we have 0 here, and 0 should be B should be after B, but B is all the B's are 1 by n's. Therefore, always bigger than 1. Now we can find a element here. So it's of the form sum 1 by m. Okay. So it's always possible, right? So because now apply arithmetic property to this number B. So what is the arithmetic property gives? There is an m in n such that B is bigger than 1 by n. Therefore just 1 by m. Just cross multiply, we get to okay, anyway, no need. So therefore now we find some element between 0 and B is of the form 1 by m, namely 1 by m. So which is a contradiction, because we know that we assume that B is a lower bound. Therefore B is less than or equal to 1 by n for all n. But if you take the specific value m, the B is bigger. So which is a contradiction to B is upper bound. Sorry, B is lower bound. So therefore our assumption is wrong. Therefore this is true. Therefore 0 is the greatest lower bound of this one. So there are so many ways to prove 0 is the GLB of this one. Now maybe I ask one question. So what is the LUB? LUB of the set 1 minus 1 by n square such that n varies in natural number. So just to substitute the values of n, what is the maximum value? What is the upper bound? If substitute n equal to 1, we get 0. If substitute n equal to 2, 1 minus 1 by 4. 1 minus 1 by 4 is 3 by 4. 3 by 4. Substitute n equal to 3, we get 1 minus 1 by 9. We get 8 by 9, like this. So what is the maximum value we'll get? So we know that actually answer is 1. So but we have to prove that the LUB is 1. So first we have to prove that 1 is the upper bound, and then if we take some other upper bound, we have to prove that 1 is smaller than that upper bound. So how to prove 1 is an upper bound? Okay, now this 1 minus 1 by n square is always less than or equal to 1. Why? Because 1 is some positive number. We are subtracting some positive quantity, namely 1 by n square. We are subtracting something from 1. Therefore, the resulting should be less than 1 by n. Sorry, less than 1. Therefore, this is true for any natural number. Yeah, got it? So, this is true for any n in n. So, from this, we conclude that 1 is an upper bound. 1 is an upper bound of the set 1 minus 1 by n square such that n in n. Now we have to prove that 1 is the least upper bound. Suppose we have some other upper bound. Suppose we take alpha is upper bound of the given set. Maybe I call the given set is A of A. Now what we have to prove? We have to prove that 1 less than or equal to alpha. To prove 1 less than or equal to alpha, because you have to prove that 1 is the least one. So suppose not. So suppose not means what? We have a alpha is strictly less than 1. Now we can find a element from A between this 1 and alpha. Suppose 1 is here. So suppose alpha is here. It is possible to find a element from x from this A. So therefore this x is of the form 1 minus 1 by n square for some n. So if you found such an element between alpha and 1, then we get a contradiction. Why? Because alpha is an upper bound. Therefore, every element of A should be less than or equal to alpha. But here we found one element bigger than alpha. Therefore, we get a contradiction. Therefore, we get to 1 less than or equal to alpha. Now, what is the element? What is the guarantee that you will get an element like 1 minus 1 by n square between 1 and alpha? So just to think about it, and then what is the guarantee that there is at least one m such that 1 minus 1 by n square is bigger than alpha? But alpha is less than 1, we know that. Alpha is less than 1, we know. And alpha is an upper bound is you know. Just think about it and then you solve it. Okay, now we start the class, and then in the next class we start about sequences.